How do you do, ladies and gentlemen, and boys and girls? I am Julius Sumner Miller, and physics is my business. And our very special business today is the subject of heat and temperature. Now, to refresh your mind on my philosophy, as in the first series, which we did on mechanics, I must say the following. This is not a lecture in physics. I propose rather to show an array of demonstrations, dramatic and exciting, in the subject before us, for the purpose of stirring your curiosity, arousing your enthusiasm, pointing up the beauty and drama of these things, so that each one of these demonstrations will invite you irresistibly to go and do it yourself with your teachers to see the beauty and the excitement that can be uncovered in these things. So, this is not strictly a lesson in physics, but rather a lesson in the excitement and drama in the subject of heat and temperature. Now, I would remind you, heat and temperature. For this and subsequent lessons, it is absolutely essential that the difference in these words be understood. And for this purpose, now, some demonstrations. Consider first the following. I have here a glass tube in which I have put a little mercury, and on top of the glass tube, some little bits of chipped glass. Then I have drawn the tube down by heating the glass, pumped out some of the air, and then sealed it off. So we have here a tube with some mercury and some little glass and largely empty space in here. Now what am I going to do? I am going to heat this test tube. Heat it. This will be my symbol for adding heat to a system, much like a candle. And I have a warm feeling for candles because my beloved friend Michael Faraday gave 6 one-hour lectures at the Royal Institution on a candle. And about Faraday I will one day speak when I do some programs on electricity and magnetism. So I'm going to heat this. And what will we see? We will see after a time the little bits of glass dancing about very energetically. So I am telling you that heat is a mode of motion. Let us do that. Here is the burner, and I am doing this with some caution because we could explode the thing and have some disaster. Now I am heating it. Wait a minute, I think I'll take another one. I see a little soot on the bottom of that other one, which may interfere with our operations. I am heating it. I am adding heat energy to it. There we are. Look at that agitation. Heat is a mode of motion. Heat energy. I have communicated thermal energy to the system. Now, who was the first one to tell us, to suggest that heat is a mode of motion? I am led irresistibly to show you a picture of one of those rascals known as the Bernoullis. And I have to see, that's the camera. That's the camera I'm playing to. This is one of the Bernoullis. And you may remember on my programs on mechanics, I made reference to the Bernoullis and did a program on Bernoulli. They were a family of over 100, all geniuses, not one an ordinary man. Now more regarding heat and temperature. Let's get over here and consider the following. Here I have 2 beakers. This beaker has a little water in it, and this beaker has much water in it. Now I tell you that if I put thermometers in these, that they read the same. Therefore, I tell you that they are at the same temperature. But is there not much more stuff here in a state of agitation than in here? Accordingly, they do not have, let me write that, unequal heat. Same temperature, but different amounts of heat. Now let's look at another pair. Here are two beakers, one with a little water, one with much water. I assert that if I put the thermometers here and wait for the time to elapse to get a proper reading, I tell you that these are vastly different in temperature. This little one has a high temperature, and this one has a low temperature. And what am I prepared to tell you regarding these? From what I have said, heat is a mode of motion. There is much more stuff in motion here than here, but here, the temperature being higher, the motion is much faster. So I could say that these have the same heat energy, the same heat energy. I hope you are getting the idea of the distinction between heat and temperature. Let me try it another way. Consider the following. Consider this. I have here some spheres of different materials: brass, lead, aluminum, iron, and so on. Now, this experiment that I'm going to do, I call virtual. Virtual. As distinguished from some demonstrations which I do, which we call real. Real ones are those I really do, and virtual ones are ones we will have to imagine. Now, I have often said that imagination is a very necessary ingredient of your life and work. So you will imagine that I have put these spheres into a beaker, and I have added some water, and I have put it on a tripod, and I have put some heat energy under it. Here it is. There is the beaker. There are the spheres in there. There's some water in there, and I apply some heat energy. And I cook them, as I would say, for a long time. Long time I cook them. Boil the water and boil the water. Will you not agree that after a time they will all be at the same temperature? The same temperature. Now what do I propose to do? I propose to take them out of the beaker with a forceps and put them one by one on a block of paraffin. And what will we observe? An astonishing thing. We will observe that they sink to different depths in the paraffin, meaning, of course, that they possessed different amounts of heat energy. Different amounts of heat energy. Different thermal energy. Different heat energy. Why? They were able to do different amounts of work. Consider the same thing viewed another way. These spheres are all steel. I heated them to the same temperature in such a beaker of water. And what do we discover? That even though they are at the same temperature, they have melted different amounts of paraffin and therefore were able to do different amounts of work. I hope you see, boys and girls and ladies and gentlemen, that I have been using the words heat and energy synonymously because they are one and the same thing. Heat is a form of energy. Now I have suggested same temperature, different heat. Consider a plebeian little adventure. Here I have two potatoes, an enormously large one and a small one. Let us put them in the oven and bake them. You are agreed that after some proper elapse of time, they are at what? They are at the same temperature. But now you know that this one has vastly more heat energy in it than this one. Same temperature, different heat energy. Or consider another. We wish to show again that heat is a mode of motion. I have here 2 beakers. This one, I say, has cold water in it, so I report to you. And this one has hot water in it, so I report. Now, mark you, I said that this is cold and that's hot, and I reported to you with my hands. That is a very unreliable report, as I shall show you in a subsequent demonstration. But what do I want to do here? I am going to drop a little food coloring in this one, and we will see the rate at which it diffuses. Then I'm going to drop a little food coloring in this one, and we will see the rate at which it diffuses there. Here we agree. Same amounts of water, very nearly. Oh, I stole a little, so I'll put it back. There we are. Since we want to do the experiment with some reliability and integrity, we will see the diffusion here, I hope, much more rapid than in the cold. Watch it. Watch it. There you see it going down so fast. I think it's going faster in this one. I do. I do think it's going faster. And hence I have shown you that there is much more agitation in the water here than in there. To sum it up in a simpler phrase, what we mean by the temperature of a system is this. What is the average kinetic energy of the little elemental parts? The average kinetic energy, 1/2 mv squared, and I put a bar over the V to mean average. What is the average kinetic energy? Now, if we take all the kinetic energies of the little particles that are in motion and sum them up, that's the Greek letter sigma, which you will encounter when you study the calculus, which means you add up all the 1/2 mv squares, and you get the amount of energy in the system. Consider another. Look at this. Very dramatic as a virtual demonstration. Here I have a beaker of ice. If I put a thermometer in that beaker of ice, you know that after a time, the thermometer will read 0 degrees centigrade. The ice is not supercooled. Accordingly, the thermal energy in this system is so much. The temperature is so much. Now let me apply some heat under here. Add some thermal energy. I am adding heat energy to the system. We see some of the ice melt, but a most remarkable thing is witnessed. Namely what? That there is no change in the temperature. So we have had change of state, but no change in temperature. And about this I shall speak on another program. Coming back to the unreliability, 3 beakers, cold, medium, hot. I put my hand so. This one feels cold, that one feels hot. I put them here, and I cannot tell you which is which, suggesting what? That the physiological determination of heat and temperature is most unreliable. So I thank you for listening to this adventure, and we shall return another day.